Okay, so today's notes are on graphs of logarithms. It's section 7.3 still, but now we're focusing more on the graphs rather than on the equations and expressions of logarithms as inverses. Now we're more directly talking about graphs of logarithms still as inverses, but focusing on graphs. So before I continue, a quick note, I didn't mention this in the previous notes. Common logarithms, this is related to what we're about to do, but more just generally related to logs. Common logarithms are logarithms of the base of 10. So, and when you're writing those, they just appear as log x. So when you write a common log, you just write it log x and it implies a base of 10. You don't need to write it. So if you just see log x, it implies a base of 10. Make sure you're aware of that when you see those or as they come up or as you're writing log to the base of 10. It's not necessary to write the base. It's implied just by writing log x. All right, so continuing. Today we're going to talk about logarithmic functions, and they are, as you know, the inverse of exponential functions, or of an exponential function, since I'm talking in the singular or writing in the singular. So what does that mean? I'm going to do a comparison of exponential versus logarithmic. So the first thing is, if we start with an exponential function, we'll use base 10, so we're using our common log. If I have y equals 10 to the x, I know inverse functions, you switch the x and y. So what I would do here to start is I'd write 10 equals, or sorry, x equals 10 to the y. And then I know I can rewrite this in logarithmic form. So my base would be 10. So I have just log, and then a base of 10, which as we know, I don't need to write, of the argument x equals the power y. So my logarithmic equation becomes y equals log x. So that's how inverse functions work, and you can have any base for your exponential and thus your logarithmic. So it doesn't necessarily need to be 10. I'm using 10 as an example, but we know that they're inverse functions. You switch x and y and you get the other equation. So this applies for graphing as well. Everything about these, the x's, the y's, are going to switch, just like all our previous inverse functions with quadratics or linear functions. The same processes apply to the inverse functions for exponential and logarithmic functions. So if I started with a table here with x and y, I'm only going to plug in two values. We'll say 0 and 1. So if I plug in 0 to x, I get 10 to the 0, which is 1. If I plug in 1 for x, I get 10 to the 1, which is 10. So if I want to make my table for my logarithmic function, I'm just going to switch the x and y. So I already have my table. I'm now going to write the y column in the x over here and vice versa. So now I already have points for my logarithmic function just by following the same processes we've been doing for inverse functions, finding the original x and y, switching them, and finding the new to find the new x and y. So we can use these to now graph, and this is an overview. I'm not writing the step-by-step out, but the main idea is when you're graphing logarithmic functions, you can start by making an exponential equation, finding some points, switching them, and finding points for your new logarithmic graph. So it's going to be a lot easier to do it that way. So write an exponential, find points, and switch them. So I'm going to make a quick graph. I'm going to leave a few lines so that I can talk about something else in a second. So as long as I have, yeah, I want at least 5 lines here. So I have my x-axis, my y-axis, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I go up to 10 here. Sorry, I'm not showing you my graph. So I go up to 10 here, and I'm going to do the same thing on this axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I go to 10 on each axis, going by ones. And if I plot my original graph, I have 0, 1, which will be right there. And then I have 1, 10, which is going to be right here. So I'm going to have a pretty steep graph. So if you sketch that, it's going to be something like this. I also, if you remember, exponential functions always have an asymptote. In this case, it's going to be at the x-axis, so I'm going to make sure that I don't cross that x-axis. And then I know the other function has a point 1, 0, and then 10, 1, so it's going to be similarly flat. And since my x and y values switch, I know my asymptote this time is going to be on the y-axis, so it's going to go the other way. So if you are having trouble seeing this, my apologies, but it goes like that. And I can check this because I know it should be a reflection of the line over the line y equals x. So if I draw that line, y equals x, they should be this just reflected over it, which it appears to be. I'm going to label them so we know. And there are our graphs. So that's how you graph them, but there's a few other features I want to talk about really quickly before we move on. So graphing them is pretty easy. You find the exponentials, switch them, find the logarithmic. But there are some other key points about exponential and logarithmic functions that you want to pay attention to. So there's the domain, the range, I'm going to try to make room for this, y-intercept, and the asymptote. So we're going to start by investigating our exponential because we've already talked about these pretty extensively in our previous notes. So I know the domain for exponential functions is all reals. Because there's no values, I'm not allowed to plug into that exponent. I can plug in whatever I want and I'll get an answer. The range though, because even when I plug in negative numbers, I don't get negative answers. I know the range has to be greater than 0 because I can't plug in any number and get 0 or a negative. So I know my range is y is greater than or equal to 0. The y-intercept in most situations, unless there's transformations, the y-intercept is going to be at the point 0, 1. And the asymptote is always going to be on my x-axis, which is when y is equal to 0. So your asymptote is always going to be at y equals 0. So these are the key features of our exponential functions. Now I know with inverse functions, all I'm doing is switching x's and y's to get my new key features of my logarithmic functions. So the domain and range for my logarithms are going to be the exact opposite. So the range of my exponential becomes the domain of my inverse. So it's going to become x is greater than or equal to 0, which works if we're thinking about this with a reflection. The asymptote needs to be on the y-axis this time. So it needs to be when x is greater than 0. So I'm never allowed to plug in a negative value or 0 into a log. So that's what that's telling us for the domain. You can never plug in a negative or 0 into a log and get a solution. The range is going to be the domain of the previous one though. So now my range for my logarithmic function is all reals. So if you think about this, while it might not look like it, this is going to go up very, very slowly, but it's going to go up forever. So your range is all reals and it also goes down forever. So your domain and range from the exponential switch. This time, again, since x's and y's switch, my y-intercept is now going to become an x-intercept, and it's going to be 1, 0 instead of 0, 1. So now, most often, unless there's a transformation, my x-intercept should be at 1, 0. So that's a useful bit of information since your y-intercept was usually at 0, 1. Now your x-intercept will usually be at 1, 0 unless it's transformed in some way. And the asymptote is similarly going to be at x equals 0 rather than y equals 0. So like I said before, it's going to be along the y-axis this time, so it's going to be at x equals 0. So it's, again, just switching your key features, so domain and range, x and y, and you now have the key information for your normal logarithmic function. All right, I know that was a lot of information and kind of lengthy, but now I'm going to have you try doing this general process on your own. So I'm going to flip the page. As I'm writing this, if you want to send me a quick email and let me know you're listening, that'll be great. So send me an email if you are listening right now. For your quick check, I want you to graph y equals log base 3 of x and determine the domain, range, y-intercept, and asymptote. So I want you to try that on your own. I'm going to go over it now, so pause it if you want to try it on your own. So the first thing I'm going to do is rewrite this as an exponential. So when I rewrite this as an exponential, I get y equals the base is 3 to the x, because again, I'm switching my x and y's. So if it helps to show the in-between, you would have x equals log base 3 of y, base power argument, you rewrite it, it becomes that. So I'm going to make my table with my x and y values for that function. So I'm going to do 0, 1, 2, 3. And if I plug those in, 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27. I'm just going to switch them for my original function, y equals log base 3 of x. All I'm doing is switching the x's and y's. So I have 1, 3, 9, 27, 0, 1, 2, 3. Then I'm going to plot them. If you want to determine these key features first, you can do that. I'm going to just graph them while we're here, or while we're doing this. So this time I don't need my y. If I'm only graphing the log function and not the inverse, if you're graphing both, you'd have to pay attention to the scale more. But since I'm only graphing the log, I don't need a very tall y-axis because y is only going to 3. So I'm just going to do 1, 2, 3 on my y-axis. My x-axis, however, I need to go all the way up to 27. So I'm going to go 3, 6, 9, 12, 15, 18, 21, 24, 27. So I'm going to go all the way up to 27 on that graph by threes. And now I'm just going to plot the points. So I start at 1, 0. So that's going to be about a third of the way to 3. And then I plot 3, 1. I plot 9. So 3, 6, 9 is going to be at 2. And then 27 is going to be at 3. So I'm going to sketch that curve, make sure it doesn't cross my x-axis since that's going to be the asymptote. And that's my graph for y equals log base 3 of x. Now if I want to write the domain range, this time the y-intercept we know is not going to exist, but the x-intercept is going to be at 1, 0. So there's no y-intercept, but there is an x-intercept of 1, 0. Your domain is going to be x is greater than 0. Your range is all reals because this is just like the last example we did. There weren't any transformations. There just was a different base to our function. So since the base was the same, I just did that. It was different. I just changed that part for my points. I didn't change the domain and range. All right. So last thing is the asymptote. And again, it's just going to be at x equals 0. So this is all my key information. This is my graph. And we've successfully finished that quick check. All right, the last thing I'm going to talk about today is the transformations of logarithmic functions. So again, I've told you transformations are not going away. So the same transformations are applied here that were applied in all our previous function equations. So I have y equals a log base b of x minus h plus k. So a is still our stretcher compression. And if a is negative, you have a reflection. So if a is negative, there is a reflection still. Your base here, b, is not a transformation, it's just the base value. So it's the value that allows you to make your table, just like we did with exponentials. It's not necessarily transforming it so much as providing the baseline that you're using. H is your horizontal translation. And K is your vertical translation. So again, these letters represent the same thing. H is still the opposite. So if it's subtracting, it's moving right. If it's adding, it's moving left. All the same types of things as we've previously seen with transformations. The only other thing I want to do is a quick example on how to graph with transformations. So I'm going to flip the page. Last thing, I'll try to go through it super quick. But in this example, I just want us to graph y equals log base 2 x minus 3 plus 4. So the main thing we're going to write, or we're going to determine exponential parent function. And what I mean by that is I don't want to deal with my transformations yet when I'm writing the exponential function, so I'm just going to look at the base. And if I have y equals log base 2 of x, which is my parent function, the exponential version of that is going to be y equals 2 to the x. So if I switch my x and y and rewrite it, I get y equals 2 to the x. So that's going to be the table that I start with. So I'm going to make a table. So if I plug in those values, 0, 1, 2, 3, we'll just do that. Then you plug in 0, you get 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So then I'm going to actually make my table for y equals log base 2 of x. So I'm going to make the table for the actual parent function, the logarithmic parent function. So to do that, again, all we're doing is switching the x and y's on the table. So this becomes 1, 2, 4, 8, 0, 1, 2, 3. And the next thing I'm going to do is now apply the determine the transformations and make a table. So it's just a series of tables. It's just a series of transformations. So here my transformations are a horizontal translation 3 right and a vertical translation up 4. So my new table for y equals log base 2 of x minus 3 plus 4 is going to be just adding 3 to the x and adding 4 to the y. So I'm taking this one table went to this table, now this table is going to this table. So I'm just going to add 3 to all my x's and add 4 to all my y's. This becomes 4, 5, 7, and 11. And this becomes 4, 5, 6, and 7. And now my last step is to just graph it. So again, all I did here was apply the transformation. So 3, since it was minus 3, it became plus. Y was plus 4, so I just added plus 4. And so my last step is to plot and graph, and then we're done. So I will do this quickly. If you need to cut out, that's fine, but I'm going to graph this really fast. So I have my x and y axes, and I'm going to do 2, 4, 6, 8. I'm going by 2s, and then my other axis I'm going to go by 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the first one is 4, 4. So 4, 4 is here, and then I have 5, 5 is going to be about there. So 1, 2, 7 is going to be at 6, 8, 9, 10, and then 11 is at 7, which is about halfway there. The only other thing I need to pay attention to, normally my asymptote is at 0, but since I translated it 3 to the right, it needs to be at 3. So there we go. There's our graph. Make sure it doesn't go through the asymptote, and you're all done. Make sure you write down any questions, comments, or concerns you have so we can go over it together.